So here I'd like to continue our study of optical instruments by looking at the camera and the eye. And the goal here is we'll first look at the camera and then use it as a springboard to discuss the eye. So this is doing the old thing where a lot of people say the eye is like a camera. One of my English professors had a great saying. He said that to say that something is like something else is also to say that it is unlike it, otherwise it would be it. And he also pointed out that the thing that you're comparing to is usually the simpler system. And this is indeed the case here. Cameras are simpler systems than eyes, but it's a good springboard. We can start with the camera and then say, okay, the eye is like a camera, except for these things that make it not like a camera. So with that, I'll just start out by saying that a typical camera lens is actually a multi-lens system. And there are a variety of reasons why you have multiple lenses in there. Some of it is to deal with things called aberrations, which we'll get into in a later video. But some of it is also to allow for things like telephoto capability by moving groups of lenses around. However, for our purposes, we can just imagine it as a single lens. That will be a good starting point. So I'm just going to draw the principal plane for our lens here, and something like that. Now, the distance between this lens here and the image plane of the camera, or well, more accurately, the distance between the image plane of the camera and the mounting flange of the lens is fixed and depends on choices that the manufacturer makes. So somewhere right behind the or somewhere right behind the lens, usually not that far in back, maybe less than 20 millimeters, something like that, will be the image plane of the camera. Nowadays, if you look at that location, what you're apt to see is a CCD array. CCD stands for Charge Coupled Device. It is a device that registers photons striking it by increasing electric charge stored in capacitors. And then the image is read off by measuring the voltage across each and every one of the capacitors, because they'll be proportional to the charge stored, which is proportional to the number of photons of light that hit it. Older school cameras that actually used, film, same sort of idea. The film would be located at the image plane. The difference is that when light struck the film, it would find a chunk, a blob of chemicals in the film, usually called a grain, and it would cause, when the light struck it, it would cause a chemical reaction to occur. And when you went through the developing process, that was how you made your image. Either way, the way that when you use a camera, you're apt to want to be able to look at many different distances. It would be very rare if you only wanted to look at one specific distance. So, we can draw a whole bunch of rays coming off here. Let's go ahead and, whoops. This ray obviously would not contribute to the image, but I'm just using it to locate a focal point here. You can go ahead and say draw the central ray. Come on. There we go. Use it to draw a central ray. And I'm not doing a very good job of making an image, are I? Am I? No. So I'm going to cheat and move my image plane to where we're going to make the image. There we go. And of course, it isn't just the special rays that contribute to the image, but literally any ray you can imagine. So all of the, come on. There we go. Say this ray here would refract like so, contributing to the image, and so forth. Lots and lots and lots of rays. So how do you achieve focus? Because as you saw when I first drew it, I cheated and moved the image plane in order to hit where I was going to be focusing at. But in practice, that's not how it works. How it works is that when either you or the camera adjusts the focus ring on the lens, it physically moves the lens back and forth in order to achieve focus. So the lens can move back and forth like this in order to bring things to focus. Now, notice too that only objects at this exact distance are going to come into sharp focus here. So why does it not look that way when you take a photo? It seems like there's what's called a depth of field where everything seems to be in pretty good focus. Well, this is because, say if I have some object over here, it won't come into focus, but say maybe it'll come into focus right back here or right in front there. And so the rays are either on their way to converging to a point just behind the image plane, or they're diverging away from a point just in front of the image plane. Now, when they land on the image plane, they're going to make sort of a circular shape like you can see in this photo here. The flower is in very sharp focus, but if you look at some of the features behind it, you can see little flecks of light off to the right of the image have been blown out into complete circles. And this is just because the rays did not come to a focus at the image plane. And so we've left this circular blob behind. How big this blob is, I kid you not, gets called the zone of confusion. And as long as the zone of confusion is smaller than a pixel element on the CCD array or smaller than a film grain, you're good. It's going to look just as sharp as something that came into perfect focus. So the depth of field is the range where you can get away with it and have a small enough zone of confusion. Now, looking to the right of the flower in the picture, you can see that the zone of confusion is quite large. And sometimes photographers intentionally go for that as an artistic effect, and they call it bokeh, B-O-K-E-H. So what can we do, say, if we want the image to be sharper than this? Well, what we can do is we can block off some of the rays that come in. Nothing says we have to use the whole lens. So this bit right here that you will have inserted somewhere in the camera lens system, it depends on the details of the design, this will get called the iris of the camera, and the hole gets known as the aperture. And this is variable. So the trade-off is that if you make the aperture big, you'll have a very narrow depth of field, but you'll let a lot of light hit the image plane. So for night photography, you might decide that that's a good choice to make. You decide to give up on depth of field to get more light hitting the CCD array. Or you might decide that you really want it way open in order to have a shallow depth of field, like say in this photo here. The aperture isn't all the way open, but it's pretty far open for this particular lens. And the point of it was to be able to focus on the squirrel. This has the effect of blowing out of focus all the greenery behind in order to draw attention to the squirrel. So this is an artistic decision. So photographers don't always go with what's going to give them the most light hitting the aperture. Now, the way you can characterize how much light gets in is what's really mattering here. So I put in the iris, I have constricted how many rays are going to hit the CCD array. And the way that this gets characterized is with a quantity called the F number, oops, of the lens. And so it's equal to the focal length of the lens divided by the diameter of the aperture. So the smaller diameter of the aperture, the larger the F number, the bigger the aperture, the smaller the F number. Now, if you look at a lot of cameras, you'll see that the choices of aperture that the lens will have available for you increase by factors of the square root of 2. This is because the area of the aperture, since it's a circle, goes the square of the diameter. So every stop, a photographer calls it, will every stop towards a smaller F number or a larger aperture, where you change by a factor of square root of 2, doubles the amount of light hitting the CCD array. This leads to what photographers call the exposure triangle. So you have aperture, shutter speed, and ISO. So aperture, there we go. Yeah, I can spell. Let's try that again. Aperture. So the bigger you make the aperture, the more light that will hit, but the shallower the depth of field. But on the other hand, it'll also make for a nice big bokeh. And with a shallow depth of field, it will also draw attention to your subject. So that's the trade-off that the photographer thinks about with aperture. Shutter speed, the longer you leave the shutter open, there's usually a mechanical shutter blocking the CCD array. The longer you leave the shutter open, the more photons of light are going to hit the sensor. So you'll just literally record more light. So you might decide that you want a really sharp image, and so to compensate for that, which means you'll have a very small aperture. So to compensate for that, you might go with a long shutter speed. And then finally, ISO is sort of the weirdest one of the bunch. It stands for the International Standards Organization. Long story behind that. But basically, it's saying how sensitive do you want to set the sensor to be. And this is true regardless of whether it's a CCD array sensor in a modern digital camera or whether you're talking an old school film camera. And with most of these sensors, you can set them to be more sensitive, more likely to record charge when a photon strikes it. But the trade-off is that there will be additional noise in the image. So usually photographers will want to keep the ISO as low as they can get away with, given whatever the scene requires for the aperture and shutter speed. If it's a nighttime, say if you're taking a picture of something at night and depth of field really matters, but there's a lot of action moving on, so you have to have a quick shutter speed, then the photographer just sort of winces, goes for a small aperture, a fast shutter speed, and then cranks the ISO way up in order to make the sensor much more sensitive, and there will be there'll be a bunch of digital noise stuck in the image that will be recorded in the image. So that's the trade-off that they will make there. Alrighty, so with that, let's go ahead and just before we segue into the eye per se, I want to just define something that'll be useful as we go into the talking about the eye. And this is a quantity called the refractive power of a lens. So yeah, you use the symbol P, but the units aren't watts here. Sorry. Some books use a capital cursive P, but not all of them. It's defined to be 1 over the focal length. And so you would think the units would be inverse meters, but usually the way you write the unit is you say the unit is the diopter. And 1 diopter equals 1 inverse meter. This is usually used in eyeglass and contact lens prescriptions. So if you have eyeglasses or contact lenses and you're reading your prescription, you'll see the letters OD and OS. OD, oculus dextris, sorry about the Latin, and OS, oculus sinistris, sorry, my Latin is atrocious. Basically right eye and left eye. So the string of numbers after right eye, the first one will be the refractive power of the lens. We'll get into what some of the other numbers might be if you have other numbers in your in your prescription. But if you have 2 lenses in contact with each other, if they're thin lenses, there is a nifty relationship that the total refractive power is equal to the sum of the refractive powers of the 2 lenses. This will allow us, say, when we get to talking about prescribing contact lenses for a patient, we can just go ahead and calculate where we need to park the virtual image produced by the park the virtual image produced by the lens, so that it'll be where the patient needs it to be. So that's a very handy relationship. All right, so with that, let's go ahead and get into the eye. And I'm sorry, but I am very much not a biologist, and so this drawing is going to be terrible. So I'm going to try to draw an eye as best I can here. Sorry. And I need a little bump right there. Okay. So this is the eye. Well, let's try that bump again. There, something like that. All right. So this is the eye here. Just work with me here, okay? This is the front of the eye, and this is the back of the eye. So this bit right here is the cornea of the eye, and actually the bulk of the refraction happens there. Then behind the cornea is the first of 2 different kinds of fluid in the eye. This fluid is called the aqueous humor. And then behind the aqueous humor is a group of muscles known as the iris. And yes, this is where the term iris in a camera came from. So this is the iris of your eye here, and this can dilate. So this is doing the exact same thing as the mechanical iris in a camera lens. It's adjusting the f number of the eye. Then parked immediately behind that, and I'm going to try to draw the shape decently. It's sort of lopsided shape. It is thinner to the front, fatter to the back. This is the lens of the eye here, and it should probably be a little bigger, but I'm sorry. This lens is attached to the walls of the eye with what are called ciliary muscles. And what this does is this makes the lens thicker or thinner. If the ciliary muscles pull on the lens, they'll make it thinner. And we remember from playing with the earlier from playing with the lens maker's equation, this will have the effect of increasing the focal length. If the ciliary muscles are relaxed, the lens will get fatter and decrease the focal length. So this is how the eye is going to bring things into focus. It's not going to move the lens, either the cornea or the lens, the cornea of the aqueous humor or the lens back and forth. The aqueous humor provides some refraction too. It's going to adjust the shape of the lens. You then form a real image on the back of the eye in a structure called the retina. And attached to the retina is one of the most complicated nerves in the entire body. It's called the optic nerve. If I remember correctly, about 1.3 million nerves are connected to the rods and cones on the retina to provide image data that gets sent down the optic nerve. So the optic nerve itself is actually pretty large and has a fair amount of structure itself, enough that it actually does some computational processing on the way to sending the information to the visual cortex in the back of the head. In fact, it will slice out it grabs about 30 frames of data a second, roughly. And each one of those frames actually gets some pre-processing done by the optic nerve. The very first bit of information pulled out, believe it or not, is velocity vectors. And if any of those velocity vectors are pointed at you, that gets shortcut over to the motor centers in the brain, which are to the front, so reducing transmission time, and you reflexively duck. So if you remember back in 3rd grade when someone threw that ice ball at you and you saw it coming out of the corner of your eye and you ducked, actually you didn't even see a picture of the ice ball yet. You just knew, hey, velocity vector this way, duck. It's actually, I want to say it's the 3rd slice of data or the 4th, something like that, comes from the rods on the retina. There's 2 different major categories of receptors. The rods are much more light sensitive, but only provide black and white information. The very last layer of data to be provided is actually the color image that comes from the cones attached to the retina. And there are 2 groups of cones that are able, between them, to provide color information. So you will form this whole contraption, just like a camera, will form a real inverted and minified image on the back of the retina. Your brain flips the image upside down, or right side up when it's processing it. Okay, 2 useful numbers to talk about with relation to the eye are the near point of the eye. This is the closest distance you can focus. And we're talking here about in young people who haven't developed any particular vision conditions yet. This number turns out to be roughly 25 centimeters. So if you try to look at something closer than 25 centimeters, you won't be able to bring it into focus. And if you say, wait a minute, I totally can, well, that's because you're nearsighted. Hold on to that thought. The other number that is worth, that we need to pay attention to is what's called the far point. And this is the farthest distance you can focus. And this should be equal to infinity. I would sometimes joke 3.2 million light years, because that's the farthest away object that can be seen by the unaided eye, which is the great galaxy in Andromeda. But that's infinity enough for us. So now, what if you've got vision conditions? Let's start with myopia. And so the patient history for myopia here is that the shape of that their eye has changed shape such that they can no longer bring images. If an object is parked out at infinity, and infinity for the eye is, believe it or not, usually just a few meters. If you got an image parked out at infinity, you can't bring it to focus anymore. So this means that the patient's far point is less than infinity. Now, this will also have the result that because the focal plane has been moved, because the retina is in physically a different location, this does mean that you can see things closer than 25 centimeters. So this is why we usually say that a person is nearsighted, because we named the condition after what's right with the eye, not what's wrong with the eye. Okay, so the prescription, if you're doing contact lenses here, is to write a prescription for a contact lens whose focal length is such that my image distance generated by the contact lens is equal to the negative, because it's going to be a virtual image because you're looking through the contact lens, the negative of the patient's far point when the object distance is equal to infinity. So working that out for using the most useful equation in optics, you can say we can remember the refractive power is 1 over f, which is going to be equal to 1 over s plus 1 over s prime. Here, s prime is going to be a negative number. S is infinity, which is going to make this term 0. So this is going to give us a negative refractive power. So this will be a diverging lens, because it'll be a negative focal point as well. Or negative focal length, sorry, as well. So if you look through a diverging lens, so if you know someone who has a single vision prescription for nearsightedness, you can go and look through their lens, and you'll notice when you look through it, the print that you're looking at behind it is smaller. This is because it's a diverging lens, making a case for situation, virtual, upright, and minified. Now, it can be the case that the shape of the eyeball goes the other way and moves the retina in the other direction than you have had for myopia. And this is called hyperopia, or farsightedness. So again, we're talking about what is right with the patient in the common English name. So for hyperopia, the patient's history is that their near point So patient near point will be greater than 25 centimeters. So you're having a hard time bringing close things into focus. So when you write the prescription, what you'll do is you'll pick a focal length such that the image distance will be equal to the negative of the patient's near point when the object distance is equal to plus 25 centimeters. So this will work out to refractive power greater than 0 or focal length greater than 0. So this will be a converging lens. So if you have access to someone's eyeglass, again, single vision eyeglass prescription, and they have and they're farsighted, then when you look through their lens, that'll be a case 3 situation if you're looking at some print close up. So you'll have a virtual upright magnified image. So you can use their glasses as a magnifying glass. All right, so let's just work a quick example of how you might write such a prescription. And then we'll talk about a few other conditions. So let's say you have a hyperopic patient. And after you've sat in the little machine going better 1, better 2, better 1, better 2, you work out that their near point is 60 centimeters. Let's go ahead and figure out what contact lens prescription they would need. So again, the lens prescription will always be written as a refractive power. So this will be 1 over the focal length. So this is just 1 over S plus 1 over S prime. So keep in mind here what this means for our prescription. This means that at an object distance of 25 centimeters, so 0.25 meters, we need a virtual image, so negative, located at the patient's near point, negative 0.6 meters. So crunch this through, this works out to be plus 2.3 diopters. So when you look at that will be the first number you see after the OD or the OS in a patient's prescription. Now, as you get older, basically after you start crossing the big 4-0, you will almost certainly develop a condition called presbyopia. And it's a fascinating name because if you break the Greek roots apart, it literally means that thing that happens to your eyes when you get old. And what's happening with a patient with presbyopia is the lens in their eye is getting hard. And so this means the ciliary muscles can't do as good of a job flattening it out. So this will push out the patient's far point, but it's not because the shape of the eye changed. So you wind up having to correct for both the fact that the lens isn't as flexible anymore and that the patient has a non-ideally shaped eyeball. So you have to correct for both things at once. The solution to that is usually, if say the patient is only having problems with seeing things up close, you just tell them to go to the drugstore and find some reading glasses that work for them. If they have other conditions, like say if they have myopia and then they pick up presbyopia, then you're going to write them for either bifocals or progressive lenses, depending on what they need. Now, if you look at a prescription and you see more than just one number after the prescription, the next two numbers are going to address a thing called astigmatism. Astigmatism is when the eye doesn't have a spherical shape anymore. It's kind of pancaked along its axis. So what you do is you add a cylindrical curvature to the lens and to the prescription lens in that case, and that will adjust for the pancaking in the eye. So the first number will be the refractive power, and the second number is the axis in degrees that for the cylindrical symmetry axis to be aligned to. Other things that you might see, or conditions that you'll run across, are cataracts. This is because the proteins that make up the lens denature over time with exposure to UV light. So it's just a matter of long enough and it will eventually become an issue. What happens is, as the proteins denature, the lens starts becoming opaque. At some point it gets to the point where it affects the patient's vision so much that what you do is you surgically replace it with a prosthetic lens. And then one other condition that you may have heard of, just to put it in there, if you've ever gone to the optometrist and they've either done the thing with the puff of air or the really scary blue light, there they are screening for glaucoma. What's happening with glaucoma is the fluid between the lens and the eye can start getting under the vitreous humor here, can start getting under higher and higher pressure, and this will put pressure on the retina and start to kill the cells in the retina. The retina is its thinnest out at the edges. So this is really pernicious because these are the ones that go first and they're way out in your peripheral vision, so you don't really notice it until it shrinks down. So when you go into the optometrist or the ophthalmologist and they do that thing either with the puff of air or that instrument that has the that puts this funky blue light through your where you end up seeing a really funky blue light, what they are doing is they are measuring the pressure in your eye. And if they notice the pressure starting to creep up, then if you haven't been seeing an ophthalmologist already, they'll probably refer you to one so that they can start looking at options for drugs to take to try to mitigate the effects of the glaucoma. Alrighty, so in the next series of videos, we will continue on looking at how to build telescopes and microscopes. Catch you over there.